We are extremely sorry for the delay due to technical difficulties. Welcome back to this session. This session will be conducted by Professor Sivaji from IIT Mumbai. We welcome Sir, and we call upon our head Department of Mathematics to present a small token on behalf of Maths Department from Somaiya College. I now invite Sivaji Sir to deliver his lecture.
For the invitation to give a few lectures in this program. I'm going to speak about 2 or 3 topics which are related. I will start with the easiest thing, which is called Pfaffian equations. Then we move on to define what's called complete integrals, and we employ this idea of solving Pfaffian equations and find methods to solve a nonlinear first order partial differential equation, which is known as Charpit method and also Jacobi method, where the number of variables is 3, independent variables is 3. So first topic is first order systems of ODEs. Usually we see equations of this type, but what are they? That's the question. What do they represent? What does it stand for? So here we have 3 functions, P, Q and R. As you see, they are functions of 3 variables. So we assume that they are good functions. So we assume they are C1 functions defined on some domain omega, where omega is contained in R3. That's a minimum, right? And to be very simple, we assume that these P, Q or all 3 functions will not become 0 at the same point, which is sometimes expressed like this: P square plus Q square plus R square at any point x, y, z is not equal to 0. This happens for every x, y, z because our P, Q, R are defined there. That's fine, but what is this equation here, which is sitting here? Dx by something, dy by something, dz by something. What does it say? Usually what we see is immediately we see these kind of things. Dy by dx is equal to q by p. I will not write the argument, obvious it is, q of xyz by p of xyz, and dz by dx equal to r by p. Of course, to do this, we need to know that p should be non-zero, so assume p is not 0. So we know that at every point xyz in omega, one of these 3 is non-zero, p, q and r, right? At least one of them is non-zero. So we assume it is p, okay? And the nature of things that we are going to do is what we normally call as local things. Therefore, if p is not 0 at one point, by continuity it will remain non-zero in a small open set containing the point. Therefore, we pretend that is our omega, and therefore p is not 0 on omega. So assume that p of xyz is never 0 for all xyz for these reasons. And this is not a bad assumption, because what we are going to do finally is always something local. So when your conclusions are going to be local conclusions, that is around some point, maybe not 2 or maybe not 3, then it's okay. You don't think of omega to be a big set and you feel you have lost something. No. So these are the things which are coming on the way. Now we can try to relate what is this 1 and 2 relation between them. Okay? So what does 1 say? 1 says that we are looking hope I'm clear now. So equation 1 is saying that they have a curve for which you have a tangent, right? It's a curve in R3. So imagine this is a curve sitting inside R3. In fact, in this example, it's sitting in omega. And what is prescribed, or what is given, is the tangential direction at any point on the curve gamma, which is PQR. So PQR. So this is the tangential direction to a curve. Now equation 2, we have dy by dx, which we are familiar with. Equation 1 we are not familiar. What is dx by p equal to dy by q? It says some things are proportional. I understand very much what is PQR, but I don't know who is dx dy by dz. What does it mean? So how we will see that, we will interpret in the next page. So here this equation 2 is dy by dx equal to q by p. That we got from the first two equations, right? So we will discuss about this 1 and 2 now. But before that, we just have a look at 2 itself and see what is this. This is actually d by dx. Equation 2 is nothing but d by dx of y and z is equal to q by p and r by p. Okay? So we have a system of ordinary differential equations for y and z in the independent variable x, and we have the right hand side, which is q by p, q of xyz by p of xyz, and r by p is r of xyz by p of xyz. So we may call them as if you want f1 of xyz, that's how it looks, the first one. Second is f2 of xyz. They are also nice functions. Why? They are the quotients of two C1 functions, and denominator is not going anywhere 0. So these are also C1 functions. Therefore, in y and z variables, they are actually locally Lipschitz functions. So for each fixed x, in terms of yz, they are any smooth function is always locally Lipschitz. So we don't have to check those conditions thanks to mean value theorem of one variable, two variables, depending on the context. Here the function of two variables. So we have a mean value theorem in the inequality form that will give you that if derivatives are bounded, you get things are Lipschitz. So this is a Lipschitz function. Normally we say local Lipschitz because same constant may not work for every yz in the domain. Okay, why am I saying this? Because now I am interested in solving some problem related to this ODE, which is initial value problem. So if you consider an initial value problem for 2 plus initial conditions, which is y at some point x0 equal to y0, and z at some point at the same point x0 is z0. Okay, so we pick up x0, y0, z0 in your omega and ask y of x0 should be y0, z of z equal to z0. So now this initial value problem has a unique solution. By Picard's theorem. Picard, there are various names, Cauchy, Lipschitz. Under various hypotheses, they have proved this uniqueness and existence. So it has a unique solution. So how do we write the unique solution? This is how one writes. It might look confusing, but let's see. Solution means a function of x, right? Defined where, for what x? Here in independent variable is x in the ODE, right? Defined for x in an interval that contains the point at which you prescribe the initial condition, which is x0. So define in an interval containing x0. This is what the theorem says. theorem is not worried about how big is this interval, etc. It says you definitely have a solution on some interval containing x0. If you are interested in bigger intervals, that is your next question. We are not interested in that at the moment in this particular lectures. That's also important. Okay. Now, see, when we write y is equal to y of x, x naught, y naught, z naught, there is room for confusion sometimes. So one could write for y, my thing is a function phi. It's a function of x. And you see, I am not putting a comma. This is the usual practice to put this semicolon. And you put whatever is inside the problem. These are the data in the problem. You are prescribing your values at x0, and you are not solving for y separately, because the equation for y involves z, equation for z involves y, right? So therefore, the other condition, initial condition also comes. This is the place at which you prescribe initial condition, these are the initial conditions. So z is equal to some other function, x, with this is the data in the problem. If you write like this, perhaps you don't have much confusion. But like this also you can write, but we will see, by writing like this, you may get into some confusion in what we write. But this is also a standard way of writing. So it's like, you know only one language, and you hear some word, in your language it means something, and you say, no, it means something else. No, don't say that. You have to learn the corresponding language, right, which you are listening, and then try to understand. So as long as you understand that this is okay, both are fine, then it's okay, even if somebody writes like this. Okay. Now, okay, we left all the Pfaffian. We have not even defined what is a Pfaffian. We just started with this dx by something, dy by something, dz by something. From there we got to this ODE. We are only doing this ODE now, right? That ODE with an initial condition, we said this is the solution. So we talked about initial value problems. Now, our equation 2, which is easy to remember, right? This system for y and z, x is the variable. So equation 2 with initial conditions. So that is our initial value problem which we solve. Now, first thing is properties of solutions of this initial value problem. Solutions of the initial value problem is a two-parameter family. So you will see these kind of things written left and right in books, and sometimes it's written 3, sometimes it is written 2, and there is a confusion. So we will see why this is two-parameter family. Because it's clear, there seem to be 3 here, right? But no, here in this problem, x0 is fixed. So we are solving for y and z, where at an x0 we are prescribing what should be my y0, what should be my z0. So these are the parameters. So y0 and z0. As you change y0, z0, you get another solution. So a solution is indexed by this y0, z0. So parameterized by this. So it's a two-parameter family. So what does this solution represents? Each solution means you have the initial value problem, y0 and z0 are there. That solution represents what? Represents a curve where y and z are going on, so in the yz plane, right? And they pass through the point y0 and z0, passing through this point y0, z0. This is happening in the yz plane. Now, in the three-dimensional space, that is, I am going to involve x also. What do you have? X equal to x, y is equal to y is a function of x. In other words, this is the graph of the solution. X, and then you have x0, y0, z0. Z is equal to. So I have 3 coordinates in R3, right? X, y, z. First coordinate is x. Second coordinate is y as a function of x, which we have determined above, or phi if you like. and z is psi of x. Okay, as x varies in the interval on which you have these functions y and z are defined, you get a curve. So this is a curve. Is that clear? Now this curve is actually so this I will not explain, you think for yourself, is intersection of two cylinders. What is that? Y is equal to y of x comma x naught y naught z naught, and z is equal to fourth part. We can obtain a parametric. What we have got is this curve x, y of x x naught y naught z naught, and z is a function of x x naught y naught z naught, right? So we obtain a parametric representation of this curve. For that, what we have to do, this is how we normally write. I am not writing the arguments for PQR. Normally people write this equal to dt, right? And you write dx by dt is equal to p, dy by dt is equal to q, dz by dt is equal to r. So you have a system of three equations for x, y and z. Now we will derive this dy by dx formula. This is chain rule, dy by dt into dt by dx. Right, these kind of things we have done in a lot of times in our plus 2, parametric differentiation it's called. Now dy by dt is q, it's here. dt by dx is 1 by dx by dt. Okay, it's not that fraction, it is the, it just means, you see, we assume p is not 0, right? So dx by dt is not 0. So it will have some sign along the solutions. So there is some invertible function in the background. So you would have seen in, if you are, I don't know the background of the students. There are students also, right? Are there BSc students? Yes. Okay, then you should have, they may not have seen inverse function theorem. They have seen? Okay. So it is that. It is not 1 by dx by dt, it is some kind of inverse. Phi circle psi equal to identity, you differentiate. Phi dash at some point into psi dash some point equal to 1 or identity. Then you can get the derivative of the inverse function in terms of the derivative of the direct function, right? So that's why it becomes 1 by p. If you notice dy by dx, I have exactly taken q by p. So these are not just manipulation, there is analysis behind it, there is reasoning behind this. Similarly, you will see dz by dx is r by p, that will come from here. Now this system, will give a name. I'll give some number, okay? Don't worry about this number. It may not be correct because I have skipped naming some numbers. We need a number to call this. So this system 8 is a system of 3 equations, right? What will be its solutions? Solutions will be functions. They will depend on x, y, z, right? And also t. All of them are actually functions of t. X and y, x, y, z are functions of t. But if you notice the right hand side p, q, r, okay, they don't depend on t. T is something that we have inserted. People have given for every point, if you call this as omega in R3, at any point x, y, z, they gave us a vector like this. I will not say vector, but a line actually. P of x, y, z, q of x, y, z, and r of x, y, z. A 3 tuple. So every point associated with some kind of direction. So this you can call direction field, vector field, whatever. Yeah, so the RHS in the system 8 does not depend on T because it's something that we have inserted. It's a very important thing. T. So any conclusions that very much depend on T, you have to be careful. In fact, so happens things, it doesn't matter. T is what is called an artificial parameter. See, if you can describe some curve, okay, this curve from here to here using this interval 0, 1, you can also describe using any other interval A to B because you know how to go from here and come back. So these are reparameterization. So now this system 8, you can consider initial value problem. X of 0 is x naught, y of 0 is y naught, z of 0 is z naught. Okay? This initial value problem will have a solution. By the Picard's theorem, it will have a unique solution because P, Q are all nice functions. But they will be defined on an interval containing 0. Okay? Around 0. Sometimes, you know, you will see in first order PDEs when you do method of characteristics. Okay? In that, what they do is they are given some initial datum curve. Through that, they pass some characteristics in a hope to find solution. Now, if you take any fixed point on the curve is generally parameterized with some parameter, yes? Through that, you will find a curve which is parameterized using T. If it, so T, of course, for that they exactly solve similar equations, system of 3 equations. Now, there you have a T. That T will be in some interval containing T equal to 0. As you change, yes, that interval will change. So that interval for which this curve is described depends on yes. Okay? So it's interesting if we can take an interval which is independent of s. But you see that there are infinitely many s's. There are finitely many, you always take the intersection, you will have the smaller one. Here there may be no smallest one. It may be just singleton 0. Intersection may be just 0. That can happen. But that does not matter, it won't happen. You can actually take Js equal to entire R actually. Js equal to entire R you can take. That is property of this equation 8 being a autonomous equation. 8 is autonomous. That's a very important property. Solutions of autonomous equations, you can assume that solutions exist for all times. Because you can do a parameterization and you will get that. Of course, parameterization will introduce some kind of constants here. It won't be PQR. Okay? It will be some multiples of PQR. But that does not matter because we are only asking for the direction to be same. So in particular 1, 1, 1 is same as 2, 2, 2. Okay? So of course there is a multiple of 1, 1, 1. But we don't mind the same line. You will find both of them on the same line. So with that point, one actually can take this. Otherwise, there are other mechanisms using which we can take Js equal to R. That we will not discuss here. But usually it is not only this, it is not even discussed in books. Okay, they will just check the most important things. This becomes important when they want to apply an inverse function theorem for some function. But inverse function theorem means we always think of some Jacobian being non-zero. So concentration is on the Jacobian, and that is not zero is actually assumed. If you don't assume, you can't do anything. So you assume that, and that is what is called transversality condition in the PDE, first order PDEs. Okay? But why I am saying that is because of autonomous, there is no problem. Even if it is non-autonomous, even then there is no problem, but doing some other sacrifice, you will find the Js can be taken as one particular interval. You can't take R, maybe. Because under reparameterization, directions change. Because you are trying to reparameterize means change this T to somebody else. Okay? But P, imagine P has XYZ comma T. That will also change. Right? In autonomous systems, P, Q, R do not have T at all. They just have XYZ. Therefore, whatever you want like this will work. That's important point. Okay. So far, no Pfaffians. It's all only a differential equation. But somehow we have some PQR, remember, PQR we have. Supposed to be tangential direction for your curve, right? Curve is in R3. Suppose you find things like this. Good ones. Okay. Then what can I say about these directions? They are perpendicular to PQR. PQR is a tangential direction. So this you may want to call it as some kind of normal directions, right? Two more directions are needed to complement one direction, so that we have a basis in R3, right? So we can think of like this. So some two things which are not like PQR, meaning not a multiple of PQR. Suppose you have got this. Now I will write this P1 dx plus Q1 dy plus R1 dz equal to 0. So dx, dy, dz, if you are not happy, you can think of this. Okay? Think of this. Now it's okay, right? dx by dt is your P, dy by dt is Q, dz by dt is R. So it says this is the tangential direction, right? dx by dt, dy by dt, dz by dt. So what I am using here is if you have a curve gamma, which is written as xt, yt, zt, this is a parameterized curve. Okay? Its derivative will be the tangential direction at any point. Tangential direction at this point will be x prime t, y prime t, z prime t. So tangential direction, somebody is orthogonal, P1, Q1, R1. Similarly, P2, Q2, R2. So we have this. R2 dz equal to 0. This is actually same thing for index 1 and index 2. Okay? So these kind of equations are what are called Faffian equations. We would have seen this in ODE, mdx plus ndy equal to 0. These are like that. But now we want to solve this. No? That's a topic about this lectures. Today's lecture will be about how to solve Faffian equations. So you have come to this. It may be easy for you to find P1, Q1, R1, P2, Q2, R2. Fine. But do you know how to solve these equations, Faffian equations? We don't know. Sometimes what happens, P1, Q1, R1 are good functions. For example, you have seen this, imagine, this kind of thing. Why I want x square? I don't need x square. Okay, but anyway, I decided not to erase, so dy plus z dz equal to 0. Suppose we have this, okay, 3x square. So this is like x cubed derivative with 3x square, right? And this is y, so y square by 2, z square by 2. Right? So I can, easily integrate this part from the exact equation that we have seen in ODEs. This is how it is, right? mdx. If you want, you can always think of a dt here so that you are more comfortable. So now everybody is a function of this t, and d by dt of this will be 0. Right? We have easily integrated this. We will see one example of this. So ma'am, what time we have to stop? 1:15. So let's look at the. So now we have this P1 dx, right? R1 dy plus, Q1 dy plus R1 dz equal to 0. Let us call solutions of this as U1 of x, y, z equal to constant. These are one writes. Similarly with index 2, you take U2. So these two together represent solutions. So if you have a function of x, y, z equal to 0, okay, this constant you can take another side. They are typically surfaces, right? So you have two surfaces. their intersection, we hope it's a curve. Our aim is to find a curve, right? So we have found curve. So it is described as the intersection of these two surfaces, the curve that we are looking for. Okay. Now let's see a very simple example. I have the notes for this, so I'll give. I don't remember from where I picked up these examples. If I find, I'll give the reference of that. I hope to find. In fact, I think there is an article written by somebody on Fabians. Some of the examples could be in this book, which you know, Professor Amarnath. So, okay, now let me. So this is how one writes dx by y minus z equal to dy by z minus x equal to dz by x minus y. Okay, so our PQR is clear, the whatever is in the denominators. Now we take P1, Q1, R1 such that this dot product with this is 0, right? And you see, you know, nice combination is there, x minus y, y minus z, z minus x. So if you add them, you get 0. So 1, 1, 1. Okay? Then the equation I am thinking of is dx plus dy plus dz equal to 0. And solution for this is x plus y plus z equal to constant. So this is one of them, u1. Now think of another one. Think of something which is simple. So here I will take x, y, z. Okay, that will also make sure x into y minus z plus y into z minus plus z into x minus y will be 0. So this is fine. Therefore, the equation I have is x dx plus y dy plus z dz equal to 0. So if you integrate, we have done this before. X square by 2. 2 you can forget because the right side I am going to put anyway constant. X square by 2 plus y square by 2 plus z square by 2 equal to constant. So x square plus y square plus z square equal to some constant. So these two surfaces describe this curve. Okay, if you notice, we had very simple PQ, PIs, P1, Q1, P1, Q1, R1 and P2, Q2, R2. Why simple? Because we could easily find a solution to the corresponding Pfaffian equations. Not every Pfaffian equation will look like this. So we will study how to solve Pfaffian equations later. Okay. Now we have to say that why this intersection represents the curve that we are interested in. Right? That PQR, why should that be tangential direction? One can show that. Maybe I will skip that part. So one application of this could be orthogonal trajectories. See, orthogonal trajectories that we normally study are some family of curves are given in R2 and we want to find another family which is orthogonal family, right? Here we are given a family of curves lying on a surface. We want to find another family lying on the surface, which is orthogonal. The surface, I mean, we may think it is like R2, but not exactly R2, right? So that will be the difference here. So what is this problem? Given a family of curves lying on f of xyz equal to 0. So this is a surface. We have family of curves which are given. The orthogonal trajectories, we normally write OT, of this family, of the given family of curves is once again a family of curves which lies on the surface. And orthogonal to the given family. So exactly the same way that we implement Orthogonal family means we have to change that slope to -1 by a, right? So the product is -1. So instead of doing the theory part, let me do the problem. So the example, my F is the sphere, unit sphere. Okay, maths courses, when we say sphere, it is the sphere. Okay, not the inside one. That we would call ball, right? Or solid sphere. And then the curve, family of curves is this. G of x, y, z equal to z minus c equal to 0. Okay. What kind of curves are this? So this is sphere cut with z equal to constant. As you change constant, you get curves. Those are circles, right? You take a sphere, cut with z equal to some constant, you get that circle. Circle, circle, circle. Now I want to find orthogonal trajectories for this. So how do we do that? The first thing is we write this, just see, you get used to this. Right? The other one is dz equal to 0. I have differentiated f and g. So now this will give us some equations like this. Dx by y is equal to dy by minus x. Dz nothing. Dz is 0. Dz is nothing. So you can switch off this. So dz is 0. So you have x dx plus y dy equal to 0. From there you get this. So therefore, y minus x comma 0. This is the tangential direction to the given curves. Okay. Now we are thinking about the other one, right? Orthogonal family. What should be that? So once again we use same notation. If you don't like, we can change the notation. Dx dash, dy dash, dz dash denote tangential direction for the orthogonal family. Then what you have is y dx dash minus x dy dash equal to 0. Maybe I should put y dash and x dash, because I'm using x dash, y dash, z dash as a variable. That's why dx dash, dy dash. So to avoid this confusion, we just remove. I don't know how to remove this. Draw, view, insert. Ah, okay. So I erase this part, okay? So you see why I am removing this. Otherwise I have to put yeah, but I think I have to put outside. So, okay, so is this not there? X y dx minus x dy equal to 0. Okay, so that is d by dx of y by x equal to 0. That means y by x is constant, c1 times x. So this is a family of orthogonal trajectories. I can't say this is y equals c1x. I have to remember the equation x square plus y square plus z square. Set of all x, y, z such that x square plus y square plus z square equal to 1 and y equal to c1x, where is c1. So that is the orthogonal trajectories. So since we have already discussed what is Pfaffian, let me just define what is Pfaffian. So definition. Is it legible? Can you read what I am writing? So it's an expression just like our mdx plus ndy. An expression of the form I is equal to 1 to d fi. Because PQ are no longer work, we are d dimension. So x1, x2, xd, dxi. Okay, expression of this form is called Pfaffian form. So this is after this mathematician Pfaff. And the equation where I set equal to 0 is called Pfaffian equation. Pfaffian equation in d dimensions or d variables, sorry. D variables. x1, x2, xd, D variables are there. So in this we will see in the next lecture in the afternoon. Now we are interested in solving them. Solving Pfaffian equations. D equal to 2 we just quickly see. Okay, it's something that we already know, but we will do it again. And in d equal to 3, so d equal to 3, 2 always you can solve. D equal to 3 under some conditions we can solve. I don't know about d equal to 4 onwards, I have not thought about this. We have to see whether these proofs will generalize or there are new difficulties. So we'll stop for now and we resume after lunch. Thank you.
Recording stopped.
Because it's two variables, we use x and y as the variables. So it will be like this: pxy dx plus qxy dy equal to 0. All the hypotheses of smoothness will continue to be there. Okay. Assume PQ or C1. Their function is two variables, so assume they are defined on some open set, open and connected set. Assume they are C1 functions. Okay. So that will be there. So PQ or C1 functions. It's an open domain. The only way we are using C1s is when we are applying the Picard's theorem. Of course, we assume that either P or Q must be non-zero at every point, which we write like this: T square x square plus Q. This is one way of writing. One can also write this. And simply like this. All three are not the same. So we assume Q is non-zero for reasons that we discussed in the morning. Okay, one of them is non-zero, let Q be non-zero at some point. We will be interested in only that domain where Q is not zero. So Q is not equal to 0 for all x, y in omega. So assume this part. as people say, there is no loss of generality. From the point of view of what conclusions we are going to get at the end of this. So that's equation 1 for now, in this lecture. And the immediate equation is the ODE, dy by dx is equal to minus 3xy by, I assume q to be non-zero, therefore this is the equation I will write. Now PQ are C1 functions, are therefore the right hand side of the equation 2 is a local ellipsis function. Therefore any initial condition, any initial value problem you pose will have a unique solution. So let us take this. Let x0, y0 be a point in your domain, and now solve y x0 equal to y0. This is the initial condition CQ. So we have an initial value problem. Equation 2 plus this initial condition. So there exists a unique solution. So 2 plus initial condition has a unique solution defined on an interval containing x0. This is all coming from Picard's theorem. In fact, Picard's theorem will always give you a symmetric interval around x0. So you have this. So we can denote y is equal to, for a change, let me do this for now. Okay? So this is the parameters. This is a solution. Let me do this. Now as you vary y0, we have a family. Family of solutions to 2, the equation 2. Of course, the moment you put initial condition, there is only one, there is no family. But as you change y0, you get a solution. So as y0 varies, we have a family of solutions to 2. Done. Now let the family be this in this form. Family means some constant, right? Of the form phi of x, y equal to constant. Okay. How do you get this? It's from here, right? From this equation, solve for y0. See, one can always give an algorithm what to do. Whether we'll be able to do, under what conditions you can do, these are different questions. Solve for y0. So y0, then y0 will be a function of whoever else is in the problem, x, y and x0. Come back and substitute in this equation. F of x, x0, psi of x, y, x0. So this is what you have, which is like this. Okay? So one does not say this, they say assume that solutions are given by this, which is in this box. The reason behind this will be this. So we know that from this step, when you want to solve for y0, you may have to sacrifice some neighborhoods. So without mentioning that, because it will explain, it will be more analytical. So instead of that, we concentrate on the method. Once in a while, we will tell what is involved. So this is phi of xy equal to c is a family of solutions to the equation 2, the ODE. Equation 2, which is dy by dx equal to minus p by q. Okay. Now what we do is differentiate this. So dou phi by dou x dx plus dou phi by dou y dy equal to 0. You may ask, what am I writing here? Loosely speaking, it is a gradient phi, there is no doubt, dot dx dy. Okay. So grade phi always represents a normal direction to anything of this type, phi of xy equal to c. These level sets, these called level sets, set of all xy so that phi of xy equal to c. So for such thing, grad phi is a normal. That's one interpretation. Or you can think that your solution is described parametrically. So x of t, y of t. Now you think phi of x of t comma y of t equal to c, and then you differentiate. Dou phi by dou x, dx by dt will come. Dou phi by dou y, dy by dt will come. Now you forget dt. So you have to understand what we are writing here. As long as you have no problem in following this, it's okay. So if you have problem, you have to think of what could that be. This in fact this that. Okay. But routinely we do this. When we see phi xy equal to c, when you differentiate d by dx, dx by dy. In fact, this is also written sometimes as d phi. So this is called, I think, differential of the function phi, which essentially means grad phi dot dx. Okay. Yeah. So dx dy. Now 1 minute. Now these are all solutions of my original equation, right? Pxy dx plus qxy dy equal to 0. Right? So this is actually pq dot dx dy is 0. Therefore, pq is parallel to grad phi. No? So that means what? Our p is nothing but some constant times dou phi by dou x. Q is some constant, same constant times dou phi by dou y at every point. So therefore C can depend on xy. Right? The constant of proportionality can be xy. So that's it. So what we have got, maybe I have written in the wrong direction. Yeah, this is the problem many times. Particularly when today morning you saw how Laplace equation is converted into polar coordinates. Okay, if you memorize, it's okay. If you want to derive that equation, how do you do it? The one which is in the background is just chain rule. Chain rule you can apply something like f circle f inverse equal to identity, or f inverse circle f equal to identity. Now the identities are in different sets. Okay, always only one of them will be useful. You can always do chain rule, but only one of them will be useful in getting this equation, the transform equation. Similarly here, this is not what I wanted, so now I will flip the things. Grad phi parallel to PQ. Okay, that means what? Dou phi by dou x is equal to some constant. I change now names into dou p by dou x. And no, P. No, P. P and dou phi by dou y is same constant times Q. Okay. Of course, here also I can say I can take 1 by C, that's right. But then you will start suspecting what C is 0 and so on. Okay. Now if I write like this, that situation does not arise, we are very comfortable. Okay, so we have got this, but somewhere, if you know that these are genuine directions, you know, that means the grad phi is not a zero vector, okay, and PQ is not a zero vector is assumption anyway, right? We want at least one of them should be non-zero. So from there we should conclude somehow that C is not zero. Once you do that, 1 by C you can take, there is no doubt, right? So you should not suddenly shift to this, but you can say, I can shift, I have some reasoning. Okay. But imagine I have started with this, very lucky, I got what I want. Now what is the equation now I have is this we have, right? Dou phi by dou x dx plus dou phi by dou y dy equal to 0, right? So that is nothing but mu p dx plus mu q dy equal to 0. But if you cancel mu non-zero, that will give you p dx plus q dy equal to 0. Right? This is our equation we started with, no? P dx plus q dy equal to 0. You multiply with a mu, then the equation look like this: dou phi by dou x dx plus dou phi by dou y equal to 0, and which is same as we mentioned earlier, d phi equal to 0. Okay, so it has become the differential expression p dx plus q dy, that part, after multiplying with a mu, has become exact. So this is what we call exact differential, right? Exact equations and so on. So this is this. In other words, p dx plus q dy has an integrating factor. You multiply with somebody, you get an exact equation. So what we have shown is, using Picard's theorem of course, is that every Pfaffian in two variables has an integrating factor. After multiplying with such a mu, you have, it is becoming d phi equals 0, therefore phi equal to constant will represent solutions. So that's the remark. A Pfaffian in two variables always has an integrating factor. In other words, you can always solve the equation. Of course, you may not know how to find the integrating factor. That's why we have several cases under which we can find integrating factor. If you are not in those cases, you don't know how to find, but it exists. That's the thing. So now we ask the same question for three variables. Pfaffian equation in three variables. So they look like this: p x y z dx, q x y z dy, r x y z dz equal to 0. This is a Pfaffian equation. So we can define, as we do in two variables, when do you want to say this is an exact equation? If you can find a function phi of three variables such that your d phi is nothing but p dx plus q dy r dz, then you can call this exact. Similarly, integrating factor. So maybe I'll write down the definition quickly. If there exists a function phi of the three variables such that d phi is equal to p dx plus q dy plus r dz, then the Pfaffian equation, this one, let's put p for Pfaffian, is said to be exact. In our previous example, that's what we did. We multiplied with x, y, z or 1, 1, 1, and we had the equations which are exact. That's why it was easy to integrate. Now we can define what is an integrating factor. A function mu of x, y, z is called an integrating factor. For the Pfaffian equation P, if mu p dx plus mu q dy plus mu r dz is exact. equal to 0 is exact. That means after you multiply the equation with some function, it becomes exact. And more, this is what we normally see people writing this. The Pfaffian equation P is said to be integrable if there exists an integrating factor. That's the meaning of integral. If you see in some dynamical systems literature and so on, there will be n notions of integrability. Okay, so it's our duty to find out which ones are same, which ones are different, and so on. So at least in this case, when we say it's a Pfaffian and integrable, it means there is an integrating factor. That's it. Now we will state and prove a theorem. So consider the Pfaffian equation in three variables: p dx plus q dy plus r dz equal to 0, where p, q are all standard hypotheses for our course, C1 functions, and simultaneously all of them don't become 0. Okay. So I have written p square plus q square plus r square, which is a function of three variables, is not equal to 0. That means it's not a 0 function. So the equality or not equality is for functions. But then there's a problem, no? If I say it's not a 0 function, it can become 0 at some places. Therefore, this is not correct. We should not do this. It's never 0. That's what we want. Therefore, better you write instead of using various terminologies. Better you write not omega R3 but omega. Wherever you find. So non-vanishing, never vanishes in the domain omega. Or this vector field PQR is nowhere vanishing. Then, so basically there are no assumptions. PQR smooth, that's the only assumption. We are considering a Pfaffian in three variables. Then the following statements are one and the same. First one, Pfaffian is integrable. So this is the Pfaffian P. Unfortunately, same P I'm using, but it's clear. In brackets means the problem is denoted by P. Brackets P is integrable. That means there is a integrating factor. Same as saying this is something that can be checked easily. It is X, where X is that PQR. Okay, X dot curl X is 0, where this notation X stands for this vector P, Q, R. So if you have P dx plus Q dy plus R dz equal to 0, and you check X dot curl X is 0, then it is integrable. You don't have to exhibit an integrating factor, you know it exists. So therefore, in principle you can solve. On the other hand, if X dot curl X is not 0, then you cannot solve this problem. So its solvability if and only if X dot curl X is 0. The curl mat, the usual thing that we do, no? Curl of PQR. Thanks for giving me a lead because I wanted to mention this. So this is how we write, no? I, J, K, dou by dou X, dou by dou Y, day bar Z, P, Q, R. I think we even write this. I don't know what, we don't do that, but we still write this. We know how to find this, no? Yeah. It's like A cross B. Yeah. Where A being the operator. Dou by dou X, dou by dou by dou X. There's an interesting thing which is useful if you are ever learning continuum mechanics. There they have a nice way of writing this. Because every time you can't write this. You can't stand with this notation and then understand what it is. And so what they have is curl of, not curl, they even have this. Suppose You take A is equal to A1, A2, A3. One of them can be dou by dou x, dou by dou x. Okay? That's how we are treating now here anyway. B is equal to B1, B2, B3. In fact, you don't have to take 3. It can be D. Then they write A cross B, the cross product. Curl is what? Gradient cross PQR, right? Okay. So A cross B. This is nothing but epsilon I j k A j B k. Okay. We know what is AJ, what is AJ, what is BK. We don't know what is epsilon ijk. Okay, and basically here I is fixed, J and K are running, right? Repeated index J and K. So it's assumed that there is summation over repeated indices. So that means essentially there is a thing which I am not written, but there is a summation over J and K for variables whichever are relevant here, 1, 2, 3. Yeah. 1, 2, 3. You have this. But the question is, what is epsilon ijk? So that also has a nice description. Anybody knows what is this? If you don't know, I will write. You have to go back and check. Okay? I have forgotten. I have learned this sometime back. So this epsilon ijk is going to be 1 minus 1 or 0. Because in curl we have minus sign also, plus sign also. Some things are not coming out. So this will be 0 if either I equal to j or j equal to k or k equal to I. Some index repeats. Okay, I, j, k, this set, if this length is less than 3. Okay, we can write it. This is easy to understand like this, right? Yeah. Then 1, if this ijk is in that cyclic pattern, like 1, 2, 3, 2, 3, 1, 3, 1, 2, ijk in that form. Any other thing is minus 1. So please check this. I don't know if there is a name for epsilon ijk. Yeah, permutations, yeah. Correct, yeah. High dimensions, yeah. So please check this. So one can define A cross B for any vectors. We know only for vectors of length 3 we defined it, but one can do this. And believe me, it's very useful in dealing with those equations. Of course, they don't write summation jk equal to 1 to 3, they don't write. You know whose contribution is that? Huh? Summation convention is introduced or popularized, I don't know what, but by whom? I think we have a picture outside. We will, yeah. I'll tell you a story afterwards. Okay, now we'll prove. 1 implies 2, 2 implies 1. So this is more like an algebra class or something. But you see, always when you have complex statements, it's better to write them very cleanly so that you actually understand. So it doesn't matter if somebody says integrable or somebody says x dot curl x is 0. Both are same. Some book may take this as a definition, who knows? But we know that doesn't matter because they are one and the same. If they are not same, then we say no, the integrability with respect to that guy is different, with respect to somebody else is different. So it gives clarity in these kind of statements. Okay, so what is 1? It is integrable. That means what? There is an integrating factor. So call that mu. So since the Pfaffian equation is integrable, that is given by 1. But what is that we want to prove? X dot curl x is what we want to do. We should not lose track of that. I am doing like the usual book. There exists integrating factor. Call it mu. Alright? So what is the property? Mu p, mu q, mu r that is nothing but gradient of something, right? So he is using gradient of u. Okay, u of x, y, z. Dou e by dou x is mu p, dou e by dou y is mu q, dou e by dou z is mu r. Okay, so this is actually mu x. This is mu x. So I think we are going somewhere. X dot curl x we want, somehow curl mu x we have. Let's see then what is curl mu x. There is nothing but curl grad u, which is 0. Curl of the gradient is 0, right? So it's 0. Curl mu x is 0. Now therefore trivially I have mu x dot curl mu x is 0. But this is not what I want to prove. I want to prove x dot curl x is 0. Okay, this is true. In fact, this is if and only if. When mu is smooth function, not 0, smooth mu not 0. This is just a computation. Please do this computation. I think the proof is also there in Prof Sivaji's book. Huh? Ah, yeah. Okay, x dot curl x is 0 if and only mu x dot curl mu x is 0 for any mu which is smooth and not 0. Because somewhere there will be a mu square factor in this computation of mu x dot curl mu x, some mu square will come out. If that is 0, you can't conclude anything of the x dot curl x. So assume mu is never 0. So therefore we have shown 1 implies 2. Now we will show 2 implies 1. 2 means what? X dot curl x is 0. We want to show that it has an integrating factor. So now I think we have to produce this integrating factor. Right? So that will be the difficult part. So this will be the difficult part of the proof. Slightly longer, but ideas are simple. In fact, one of the ideas which is going to come now is part of some of the methods to find solutions to Pfaffian equations in 3 variables. So we are going to restrict our attention only to 3 variables. So 2 implies 1. Now first thing is treat z as constant. See, don't ask me why. Maybe because I am comfortable. Once z is constant, 3 variables becomes 2 variables. So I have some plan. In the end, I am responsible to show that Pfaffian is integrable. Right? You catch me there. So this is how it is. Do what you want. You get something and show that that serves your purpose. Now once that serves your purpose, now you can explain what you have done is alright or not alright. Doesn't matter. Finally here what matters is the end, the answer. Once you get the answer, it's fine. So that is true of any mathematical problem or any problem for that matter. Right? Don't bother whether is this differentiable. Don't ask this question, you will be stuck there. Bindas you do integration, differentiation. The trouble comes only when you get what is good or what is correct. Because now you have to justify it. If you are not able to progress, it's okay. Right? Okay, so this is what we do. Treat z as constant. So my equation, the dz will drop. So I have z there, but as a constant. No variation in that. This is what I have. Now, z is a constant fixed somewhere. So you have essentially a Pfaffian equation in 2 variables, which is integrable, which means there is a solution you can assume. You can assume that there is an integrating factor, whichever way you want, whichever way is going to be useful for the later things. So here what I am going to do is, there exists this, I don't know what I should call it. I call reduced Pfaffian. This RP is a Pfaffian in 2 variables. Therefore integral. This we saw beginning of today's class, in the afternoon class. So 2 variables. Therefore there exists an integrating factor, and of course a solution. Dou u by dou x is equal to mu p, dou u by dou y. Okay, and solution to Rp is given by I don't know why I have written this, but it doesn't matter actually, whichever way you write. U of x by z equal to c1 z. Z is sitting somewhere, right? So anything, any constant that you get will depend on z. May depend on z. You can't say it's independent of that. That requires a lot of guts. I say, it depends on z. Keep it. So u of x by z equal to c1 z. The solutions. If z was not there, it's like phi of xy equal to constant, right? For the Pfaffian and two variables, solution looks like phi of xy equal to constant. The same thing here, but because z is there, we incorporate z everywhere we want. Now, with this, what I want to do is I want to go back to my original Pfaffian which is given, p dx plus q dy plus r dz. I am going to multiply that with a mu. I am free to do it, I will do that. 0 is equal to mu p dx plus mu q dy plus mu r dz. This is the equation. Now mu p is dou e by dou x dx. This is dou e by dou y dy. Now what I do for mu r, I add and subtract dou e by dou z. Dou e by dou z dz. This is not there above, so I subtract that. So mu r minus dou e by dou z dz. Okay. Of course, first thing you actually should ask me is this Rp is a Pfaffian in two variables. There is an integrated vector, I know, and there is a solution, I know. Z is hanging as a parameter. Xy is what is smoothness is what I can guarantee. Why is it differentiable with respect to Z? Right? These kind of questions should be asked. And I think how do we guarantee that? Why is it it depends on Z in a nice way, differentiable way, right? In general, things are not like that, no? You have a problem, which is a parameter, you have solution. If problem depends nicely on the parameter, why should solution behave nicely with respect to parameter? These are nice theorems. These are available for several classes of problems. One of them is ordinary differential equations with Picard setup, initial value problems. Solution depends smoothly, as smooth as the dependence of the problem. So because of that, this you can take to be differentiable on Z. Okay, this is very important. Similar things are not true in eigenvalue problems. Eigenvalue of matrices. Matrix depends nicely on the. Okay, since I mentioned, let me just do a detour to that. Suppose you have a thing like this: x minus x 0 0. This is a lovely matrix. Eigenvalues are x and minus x. Correct? But normally nobody cares x and minus x. What they care is first eigenvalue, next eigenvalue. So in this case, eigenvalues will become lambda 1 of x equal to minus mod x, lambda 2 of x equal to mod x. Okay? So if you see the picture, say somehow pictures are incomplete without writing y-axis. So one is this, other is this. Okay? This is your lambda 1 because this is a smaller one. This is your lambda 2. But it has good description also. That let us call mu 1 of x equal to x, mu 2 of x equal to minus x. This is a beautiful description of the eigenvalues. Right? Smooth description. Whereas if you insist the order lambda 1 less than or equal to lambda 2, smoothness is destroyed. But at least something better. You can describe eigenvalues as nice functions thanks to forgetting the order, right? This is one variable. Two variables, even this is not possible. We can imitate the same example. The example is this. I think this is one, for which eigenvalues are plus or minus root s square plus y square. Okay? So, you have problem. And you cannot even rearrange so that you have good dependence. That's because both the cases, here at x equal to 0, the trouble is at x equal to 0, right, for the ordered ones. What is happening for x non-zero in this matrix? They are simple eigenvalues. X equal to 0, multiple eigenvalues. So multiplicity is a problem. But because x is only one variable, it can be overcome. Here again, when x, y are 0, there is an origin, multiplicity is 2. If you are away from origin, each eigenvalue is multiplicity 1, simple eigenvalue. But the problem here is the number of parameters is more than 1. This is where the perturbation theory, this comes under perturbation theory, changes. So this is a bad situation. This is a good situation. Our ODEs are always a good situation. Okay? So don't think that problem behaves nicely on the parameter, therefore whatever you are interested also behaves nicely. No. That much is not to be expected. Fine. So the computation we have done is fine. Now this is a nice guy, right? Because this is precisely du. Du. Dou by dou x dx, dou by dou dy, dou by dou z dz. In fact, in exact equations that we do in ODEs, this is what we do, no regrouping. And so, but there is a culprit here. Somebody extra guy is there. We have to handle this. So this is like du plus somebody into dz. That looks good. Du plus somebody, I will call him k, dz equal to 0. Alright, once again a Pfaffian in two variables. Don't jump, because in Pfaffian two variables means the coefficient function should involve only those two variables. Here the coefficient for du is 1. Fine, no problem. What about k? K is actually k is actually what? The original one which was there, mu r, mu of xyz, r of xyz. This is mu r minus dou u by dou z, which again depends on xyz. So this is not a Pfaffian in two variables. If it were, no, we are done. So we need to do something. So we will work on this k now. So far we have not used x dot curl x is 0. Right? That will come somewhere. So our mu x, that is mu p, mu q, mu r, is mu p, mu q, dou u by dou z plus k, right? But k is precisely mu r minus dou u by dou z. This is actually mu r. The notation k was given like that. So this is mu x. Now we will use mu x dot curl mu x is 0. Use mu x dot, mu is a good function. Mu x dot curl mu x equals 0. How can you use this? Because we are given x dot curl x is 0, and because x dot curl x is 0 is given to us, and x dot curl x is 0 is equivalent to mu x dot curl mu x is 0. And its equivalence with mu x dot curl mu x. So I will use mu x dot curl mu x is 0. So I will compute now curl mu x. So what is curl mu x? This is another one, curl. What is mu x? mu x is, so let's observe what is mu x. Mu x is nothing but yeah, I should have started with mu x. I have written on the top, so I'll continue and write it. So here let's observe this. Mu p mu q dou v by dou z plus k, that is mu x, and this is nothing but mu p is what? Dou v by dou x. Mu q is dou v by dou y, and this is dou v by dou z plus k. Right? But that is nothing but, so mu x is equal to gradient of u plus 0 0 k. Okay? So therefore curl mu x is nothing but curl grad u plus 0 0 k. Okay? So this is nothing but curl grad u additive and curl 0 0 k. But curl grad u is 0. So this is just curl 0 0 k. Okay, so curl mu x is simply curl 0 0 k. Now mu x dot curl mu x is 0. So zero. Okay. So at the end of this, what we have, mu x is once again grad u plus 0 0 k. No, yeah. This is grad u plus 0 0 k. Right, that's what we have determined above. Mu x equal to grad u plus 0. Dot curl 0 0 k is what we want to find, and curl 0 0 k is nothing but dou k by dou y minus dou k by dou x, comma 0. This, so this, so correct, this is equal to this. So please, just computation, please do that. So mu x dot curl mu x is 0, so we have got to this. So we got this relation. And if you expand this, what you have is dou u by dou x, dou k by dou y. Okay, because this is dou u by dou x, dou u by dou y, dou u by dou z plus k. And that part with 0, so third one is not affecting. So what you have is dou u by dou x, dou u by dou y dot this. So dou u by dou x, dou k by dou y plus dou u by dou y into minus dou k by dou x equal to 3. So this is nothing but a certain Jacobian 0. This is a notation for the Jacobian uk with respect to x and y. Okay, so this is nothing but just this statement ux uy kx ky. So that is 0. That's precisely the expansion. Now here we use a result. The result says that the moment you see a certain Jacobian like this is 0 everywhere, not just one point. This implies that there is a relation between u and k which is 0. There exists a relation between u and k of the form. That means they are not two genuinely independent people. Okay, they are dependent on each other. So this notation is h of u comma k equal to 0. So this is a result in Professor Amarnath's book with a small condition. You have to assume that dou k by dou x is not equal to 0, or any one of them. Dou k by dou y is not 0, or dou e by dou x is not 0, or dou e by dou y is not 0. Because this Jacobian is symmetric, right? You write uk or ku, it will be 0. So therefore one of them should be non-zero, then only this is true. No, then only it's true there is a problem. Then this is true. That's the hypothesis. But I don't know whether we are in a position to check that. So please check this. Can we apply the theorem? So this is another thing. When you are applying a theorem, you have to make sure that you satisfy the hypothesis of the theorem. Right? Otherwise it's an unauthorized use of theorem. Okay, so what is the end of this? What we have? H is independent of x and y, but everywhere there is a z in the background. So this H independent of x and y, but may depend on z. So now what we have is that equation du plus now k of u comma z dz equal to 0. Okay. This together, k is here. So I am saying k can be written in terms of h and u or something, and z, because z is in the background. So once again there is some kind of implicit function being done here. So this is what happens. And now we have a Pfaffian in two variables. Because you have a coefficient here, it's 1, and here it depends only on u comma z. So you have Pfaffian in two variables, therefore it's integrable. Therefore you have an integrating factor and you have a solution. Now that solution will be looking like some function of u comma z equal to constant. Now u you already have solved before. Right? How this u is coming from? In the step 1 where we treated z as constant. Here. This is where I got u. So now you substitute for u, you will have the answer. So that's the proof of this result. So solutions to du plus kuz dz equal to 0 given by some function phi of u comma z equal to constant. Now you go and substitute for u, which is u of x, y, z. So you have got a solution directly. So this shows Pfaffian is integral. So the idea is not to waste our earlier effort of doing two variables. So reduce to two variables and get it. Now we will discuss 2-3 methods which are very, very simple. Let's do quickly. In fact, we have already seen before. So there are few easy cases in which you can solve Pfaffian equations. First is when curl x itself is 0. Okay, we know the equivalent condition now. If you are given pqr dot dx dy dz equal to 0, to decide whether it is solvable or not, whether we should be interested in solving it or not, we have to check, call pqr as your x, verify whether x dot curl x is 0. If curl x itself is 0, imagine, then there is nothing to verify, it is always integrable. So that's the simplest example. If curl x is 0, it means x is of gradient type. Right? Then done. So you have p dx plus q dy plus r dz equal to 0, and this pqr, curl x is 0, this is x. Okay? Curl x is 0 implies, if and only in the spaces that we are working with, it looks like gradient of some phi. Okay? What does it mean? Therefore it is solvable. Now, how do I know that phi, right? X equal to grad phi. If I knew the phi, we are done. But how do you know what is that phi? So still we are do something. Now here, it's now tricks. Your abilities will come here in the picture. So now I take x square common. This is a trick. It works only here, and I don't remember. That's why I'm actually taking from the book and writing. With experience, you may be able to spot more such things. There is no algorithm to find that phi. At least in two variables we have an algorithm to find. Right, the integrating factor, all that we can find. But here you can't. So you have got this. Now this is x square into d of xz, a product xz. Oh, something is done. Now 3x, 3 no 3. 3y square is 1 go. So that is y cube, x into dy cube. I hope these things are fine. Oh, but minus y cube dx, I don't know what to do. That's a problem, huh? Oh no, first thing is to divide with x square everywhere. So this is not the way. Divide with x square, then what you have is z dx plus x dz. When you divide here 3y square by x dy, and here you have y cube by x square. Huh? Yeah, we'll come back, yeah. So this is nothing but d of xz, that's the first two terms is d of xz. Next one is d of y cube by x. So therefore, xz plus y cube by x equal to constant. Okay. The other case is so-called variable separable, where p depends only on x, q depends only on y. These are much easier to do. So the answer will be just integrate this. Integrate this, integrate this, integrate this. That's what we did, no? X dx means x squared by 2. So integral p plus integral q plus integral r. We don't have to mention. These are integrals with one variable equal to constant. So I will not do this example. I will give you the notes. No? Then another important thing is one variable is separable. I don't know when I have to stop. 10 minutes? No, time is up. Harsha may be coming now. Okay. So basically I have in this, I have two more cases and then one method. Maybe I will discuss that in the next class. Yeah. One variable separable I will do. So one variable separable means what? One day comes separately. Pxy dx, it's not mixed. Qxy dy. So far it looks like only two variables. The third guy will come but he will sit separately. Rz dz. Okay. Once again it is integrable if and only if x dot curl x is 0. So integrability condition is x dot curl x equal to 0. That condition gives us r into dou q by dou x minus dou p by dou y equal to 0. So assuming that r is not vanishing, anywhere, so we get dou q by dou x minus dou p by dou y equal to 0. Okay, this implies p dx plus q dy is exact. So this implies this is actually exact. Implies, this is a condition for exactness, no? So our life is easy now. Because we actually have the part which does not feature z is already exact. Thanks to the integrability condition of the three variable fashion. Implies this p dx plus q dy is exact. Otherwise we know p dx plus q dy alone we can solve. But then we may have to multiply with some mu factor, integrating factor. Now there is no need to do that. If the 3 variable fraction is solvable, which is here, it's automatic that pdx plus qd is exact. So easy. So now this will be, so pdx plus qdy will be du. Now it's straightforward. Du plus rz dz equal to 0. Now this is the previous case where variables are all separated. Right? This depends only on z, this depends only on u. In fact, it doesn't even depend. So therefore we can integrate this. So I give one exercise to you. Please do this. See, it's not that automatically it is of this form. You may have to divide with somebody. You have to spot the correct combinations. This is what our students have to do in the exam. No? A is some number. Okay. First you divide with those factors, y square minus a square minus z square. You get good form. So divide. First step is divide with y square minus a square into x square minus z square. Don't worry, just divide with it, then you will be in a good position. In case you want to know the solution, answer is x square minus z square into y square minus a square equal to constant. This is the answer. So I'll stop for today here. Tomorrow I will resume with this and we move on to complete integrals. So we have seen reasons why we want to study Pfaffian equations, right? Which was just a system of equations, ODEs. Are we still online? Okay. So if you have any questions, please write to my email ID. I will respond to you sometime or the other. Sivaji, sivaji.ganesh @gmail.com.